The main thing required by any IO device is either it is trying to provide you some input or it is asking you for some output. In case if it is trying to provide you some input, then it is putting that input in a register and you have to read it into your registers, right? So the heart of the problem is you have to solve this problem by executing either INP or OUT like this. We have already seen these two instructions when we are discussing about the design. So the heart of the problem is you have to execute INT or OUT, right? This means that you have to read the input from the input device or you have to send the output to the output device. Now, without doing these two things, or in order to do these things, when we are looking at this interrupt system, we have to do many other things. So everything which is not involving these two instructions is called as overhead, isn't it? A input device is providing you some input and you should directly read it by using the INP command, but without doing that, instead of doing that, we are doing many other things, right? And finally, at the heart of the interrupt service routine, yes, we are going to doing this, but then before doing these instructions, we are going to do something, and after doing these instructions, we are going to do some other actions. This everything put together is called as overhead of the interrupt system. So what happens because of the interrupt is most of the things like finding out who has raised the interrupt and then deciding who has to be serviced first, that is priority. Everything is done by hardware, and so you need not consider it as a overhead because you are not wasting any time. Hardware is fast, and while you are executing something else, everything will be provided by the hardware. But then after that, once the interrupt has been raised, then you should stop executing your program, which means whatever program you have been executing, you have to stop it and then deviate from that. From there the overhead starts, right? So what happens first? Whenever you get the interrupt, what happens first? Let's say you have completed executing your current instruction. After that, again you are going to get T0. Along with T0, if the interrupt flag is also set, then instead of triggering the instruction cycle, I told you that we'll trigger the interrupt cycle, right? If you remember, that is what we discussed in the design, right? Instead of entering into the instruction cycle, we are going to enter into the interrupt cycle. Now what will be done in the interrupt cycle? Interrupt cycle is completely executed in the hardware. It is very fast, probably 2, 3 or 4 clocks, but then it is very fast. It will just take the same time or at almost the same time as taken by the one instruction. So it is not a very big overhead. Unless until we get into the interrupt service routine, whatever happens, it will happen fast. See this. Now when you enter into the interrupt cycle, I hope you are understanding this. When will the interrupt cycle start? Your current instruction is over and you are about to fetch the next instruction, but then you have found out that there is an interrupt request, and then instead of fetching the next instruction, you will go into the interrupt cycle. Now what should be done what should be done in the interrupt cycle by most of the computers? See this. So first thing is SP is SP minus 1. So in order to understand this SP, that is stack pointer, you have to understand how this stack is implemented. Okay, now assume that this is the memory. Okay, generally stack will start somewhere. Let's say this is the stack and it will grow upwards. This may be the address 0, this may be the address 1, this may be the address 2, this may be the address 3, so on. This may be address 1000, this may be the address 1001. So stack is going to grow up, right? So if your current stack pointer is pointing to the address 1000, it means that it is the top of the stack and it is already filled with some data. Therefore you have to go to the next location here and you have to place whatever you want to store there. I told you that we are going to store the return address in a stack so that it will be useful for us in case if there is any recursive function calling, right? Or in case if one function calls other and that particular function calls others. So function calling, if it is nested, then it is always better that you implement using a stack. if you are trying to store the return address at a fixed location, you will not be able to implement recursive calls or a function calling the other function. Got it? That is why we are going with the, most of the computers will go with the stack. See this. Now stack pointer is decremented, okay, which means from here we will be pointing here, and into the memory which is pointed by the stack pointer we are loading the program counter. What will the program counter contain? See, somewhere you are in the program, let's say you are executing the program, and let us assume that you are currently executing the program and the instruction that you are executing is at address number 100. When you are executing this instruction, when you have just finished the execution of this instruction, obviously program counter will contain the address 101, isn't it? But then without going to 101 and fetching the instruction at 101, we have jumped into the interrupt cycle without getting into the instruction cycle. In case if you would have jumped into the instruction cycle, you would have started with fetching the instruction at 101, isn't it? But then we are not doing it here, so we are jumping into the interrupt cycle. Now therefore program counter will contain 101. So when you are going to some other place and executing that interrupt service routine, and whenever you come back, you have to again start executing from 101. That is why whatever is present in program counter will be storing it there. Let us say 101 is the return address, then we will store 101 in this location, 999. Got it? And then we are going to release interrupt acknowledgement as 1. So interrupt acknowledgement has various functions. It is also used to convey the device that yes, your interrupt is currently being processed. But in our implementation, if you see the last diagram in the previous video, if you see that diagram, there interrupt acknowledgement is actually connected to a register, right? And that register is connected to the CPU, and the main purpose of that register is giving the address of the interrupt service routine. Now in most of the computers, how it will be implemented is, we have seen it, the register is having many bits, and now we are the encoder, that priority encoder, you please refer to the diagram, the priority encoder is providing us with 2 bits, X and Y, isn't it? Let's say this is X and this is Y. In case if it is a hard disk, interrupt is given by hard disk, then it will be 00, right? Otherwise if it is a printer, then it will be 01. If it is a reader, then it will be 10. If it is a keyboard, then it will be 11. Got it? So now if you see this, all the remaining bits are already filled with zeros, right? So what does it mean? In case if the interrupt is given by a hard disk, the address which will be generated or provided as a vectored address is all zeros, right? And now this address will be sent to the CPU into the program counter, isn't it? See, now program counter is loaded with that vectored address. What does it mean? In case if it is given, if the interrupt is raised by hard disk, your program counter is going to get all zeros. Then in this particular address, we have to write the code which will be the ISR of the hard disk. But if you see the next one, in case if the interrupt is raised by the printer, let us say this one 01 is printer, then you are pointing to the address 01, which means this one, right? So if this part ISR of the interrupt service routine of the hard disk is going to start, it is impossible to start the next program here, ISR of the printer. Therefore we are not actually going to put the ISRs at this location. What we'll put here is the address at which that ISR is present, right? So similarly, if it is reader, we will be going here 210. If it is keyboard, we will be going here, which means 11. Got it? So at some fixed location, we are going to place the address of the interrupt service routine. So what should we write here? So when do we think that we'll come to this, we'll execute this instruction? When the interrupt is raised by hard disk. Therefore you have to put the instruction here, jump followed by address. What address it should be? The ISR of the hard disk, isn't it? So you have to actually put that number, but then I'm just writing the word this means in this place I am going to put that particular number, and if you go to that particular number, there should be the ISR of the hard disk. Let us say the ISR of hard disk is here, ISR of hard disk is here, right? And if its address, let's say it is 500, then you are supposed to put jump 500, right? So whenever an interrupt is raised by the hard disk, automatically the address will be provided by the encoder. That is why it is called as vectored addressing, right? Vectored interrupt, which means the interrupting device is also providing you with the address. Now this address will be stored in the program counter, and so program counter will start from the next instruction starting at this particular address, and when it goes to this particular address, it will understand that, oh, I have to jump to this particular address. Got it? If you see this, it is clearly mentioned here, right? Okay, now similarly here there will be jump. So where should you jump here? To the ISR of the printer. I'm just writing it, right? So here the appropriate address of the ISR of the printer will be written, and what should happen here? Jump ISR of the reader, jump ISR of the keyboard, right? So like that, if you have, let's say, 8 devices, then the first 8 locations will be filled with that. Then the encoder will supposed to give you 3 bits. Got it? If you have 8 devices, see, in case we had discussed the example with 4 devices, that is why we have an encoder which is having 4 inputs and 2 outputs. In case if you had 8 devices, then your encoder will be having 8 inputs and 3 outputs. Got it? That priority encoder. Okay, somehow we are able to reach here. So everything that is done till here, right, is done in the hardware, and that is called as interrupt cycle. Got it? This entire thing is done by the interrupt cycle. Now before you start the interrupts, you try to interrupt service, you try to disable this. You have to disable this particular interrupt facility for some time. The reason why we are disabling the interrupt is it will be ambiguous. Let us say you have just finished the interrupt cycle and you are about to get, and you again got T0, and by that time if some other device again raises the interrupt, then instead of getting into or crossing this particular interrupt completely, we'll again get into the interrupt cycle and do it, and it will be ambiguous. So the last step is you disable the interrupt for some time, again we'll enable it. Okay, understood till this point? So entirely whatever is done here is done in the hardware, and it is called as interrupt cycle. So even though till now whatever we discussed is completely based on the hardware, we need to have the actual software which will do the work, right? So even though I am saying that this particular daisy chaining and the parallel priority interrupts are hardware based, it doesn't mean that there is no software involved. Ultimately software has to come into picture. Now the software will come into picture. Now see this. So after finishing this all interrupt cycle, then again you are going to make IENA 0, which means there will be no interrupt after this. So when you get T0, you will start executing the fetch phase, isn't it, of the instruction cycle. So after this we are going to get into the instruction cycle, and in fact we are going to fetch the instruction which is pointed by P0, that PC, program counter. And what will program counter contain? It will contain the some address in this part, isn't it? And so from there we will start jumping to the concerned this interrupt service routine. So let us say the device which has caused the interrupt is a hard disk. Then from here when you execute this particular instruction, you know what jump will do. Let us say it is unconditional jump. Jump will just replace the program counter. Instead of getting 1, it will just replace the program counter with 500, which means it will jump to the appropriate ISR of the hard disk. Now since we have reached this interrupt service routine, what are the things we are supposed to do? So the heart of this ISR is to provide the service to the hard disk, but before you provide the actual service to the hard disk, you are supposed to do some bookkeeping work, and after providing this service you are supposed to provide some bookkeeping work. Now what is that work? So see this. So initial operations of ISR, it is completely a overhead. It is also sometimes called as overhead. The initial operations which we do in an ISR is a overhead, and the final operations which we do in an ISR, both are overheads, right, which will actually decrease the efficiency of the computer, isn't it? Because it is completely useless. but still we have to do this. Now see this one. First one is clear lower level mask bits. So why this thing is implemented? Because if you are implementing the ISR of some device, the low level devices should not disturb it. For that reason we are going to clear the mask bits. So you know what the mask bits are, right? You please refer to the previous diagram. There you can see the mask bits. In case if you are providing the service to the hard disk, all these 3 bits which are related to printer, reader and keyboard, they have to be set to 0. That is the meaning of it. In case if you are talking about the printer, if you are providing the service to printer, you have to clear only these 2 bits, reader and keyboard. You need not clear this one. That one has to be left as 1. Why? Because if you are executing the interrupt service routine of printer, hard disk can interrupt you, right? So what is the logic behind it is, when you are executing the interrupt, when you are providing service to a low speed device, suddenly when a high speed device comes and asks for this service, you can go to the high speed device, and since the device speed is very high, you can provide the service to the high speed device very fast and again get back to the low speed device, and it will not actually hurt low speed device at all, because the time, if you compare, the high speed device will require only small amount of time for this service, but the low speed device will require lot of time. So you can think of it this way, maybe this one may take microseconds, this one will take milliseconds, like that. Okay, so that is why we are always going to let the high speed device interrupt the low speed device, right? And that can be done by using this interrupt service bits. And next one is clear the interrupt status bit IST. So if you remember this, we have a flag called IST, right? So that indicates that there is some interrupt. So for some time you just clear it, because we are already servicing an interrupt, we don't want to see it now. Okay, and now save the contents of the processor registers. So this step is very important. So actually this particular step, the implementation of this particular step varies from computer to computer. Some people say that it is better to implement this particular step as a part of the interrupt cycle, which will be implemented in the hardware, because it will be faster. Some people say that no, leave it to the ISR, it will take care of it. But the problem with leaving it to the ISR is, you have to write this step in all the ISRs. Instead, if anyway, whenever there is an interrupt, if you will always have to save the context, isn't it? So I think you know what this is. It is the context of the processor. So if the processor is executing a program, whatever are present in the registers, they all have to be saved at some point, right? And later when the program resumes to that particular point, then you have to load the registers with those points, so that there will be no ambiguity. Otherwise, if you don't store and restore the registers, there will be ambiguity, because the program which is currently executing, it might think that the registers are not modified, and it will try to use the values in the register which have been modified by the interrupt service routines. That is why we are supposed to save them somewhere and again get them back, right? But then there is a lot of different people have different opinions about this step. Some people say that you please implement this as a part of the interrupt cycle, because it is going to save a lot of time if you are going to implement it in the hardware, right? And also the other reason why they say is, instead of, if you are going to leave it to the ISR, every ISR has to include it. For example, interrupt service routine of hard disk should include that part of the code. Similarly, everything has to include it, and memory has to memory will be large, and this time taken for these steps will be more compared to the hardware. But then if you try to implement it in the hardware, you will have to increase the hardware cost. So there is always a trade-off. If you want it to be fast, you put more money and get better hardware. Otherwise, if you want it to be cheaper, then implement it in the software and go step by step, right? So what will this typically contain is just store instructions. You are going to store each instruction, whatever that each register into the memory someplace at some point. So they'll contain a sequence of store. So it depends on the number of registers you have. If you have 10 registers, you have to store all the register values into the memory. Got it? And the next one is set interrupt enable bit IEN. So why should we set it? Because if you remember, we have actually disabled it, isn't it? We have disabled it here. Now if you don't set it back, then what happens is no interrupt can be seen by this particular interrupt service routine. Let us say currently it is the interrupt service routine which is providing service to keyboard, and suddenly there is an interrupt from hard disk. If you don't set this, you please see the the diagram. The AND gate will be getting as its input. One thing is the input is provided by the encoder, and the other one is IEN. If you don't set IEN back, then there is no way you can see or CPU will get an interrupt. So that is why you have to set it back. You disabled it here because you don't want any ambiguity till everything is being saved and everything is safe. So here everything is being saved and everything is safe. Now you can be interrupted. Got it? So once everything is being saved and you are safe, now you let someone to interrupt you. So at this point, now you go to the heart of the service. So what is the heart of the service? That depends on the device. If it is a keyboard, we are going to just read from that particular register into the memory. If it is a hard disk, we are going to read from that particular register into the memory, and we will be in a loop. Got it? So now at this point you are allowing the interrupts to come. So when you are executing the low level ISR, high level ISRs can obviously interrupt you. Got it? Now this is all anyway overhead, but it is required. Now let's look at the final operations. Final operations means, let us say you have performed whatever service is required by the device. Let us say the service required by a device is shifting some words from the keyboard registers into the memory registers. Yes, you are done with that, and now you are going into the final operations. Now what should the final operations contain? So before you perform all this, again, just to avoid the ambiguity, we have to do some certain things. Clear the interrupt enable bit. So while you are returning, you don't want any interrupt to happen because it will lead to some ambiguity. So temporarily you just switch off the interrupts, and after switching off the interrupts, now restore the contents of the processor registers. Why? Because you are returning the control to the program which was running before this interrupt service routine. And now clear the bit in the interrupt register belonging to the source that has been serviced. So if you remember, for every source we have given one bit in a register, interrupt register. Now you go there and clear it. If you don't clear it, again, even though it has been serviced, we will again fall into this entire loop once again. So clear that one, make it 0, so that you are giving the opportunity to that device to again raise an interrupt. Otherwise, you'll think that even if it doesn't raise an interrupt, you'll think that it is continuously raising an interrupt. That is why you clear it. Yeah, and now set the low level priority bits in the mask register. So earlier, when you are actually providing service to the higher level device, you have turned off or cleared in the mask register, you cleared the bits which are which belong to the low level devices. Now you again set them so that everyone will get a fair share. If you don't do this step, once you have cleared the bits here, where did you clear it? Yes, once you have cleared the bits here, no one is going to set them, and no one will ever listen to those devices. So just to give them back their fair share, you just set it. So once you have performed the high level interrupts, whatever low level devices are there, give them the share. And then restore the return address into PC and set IEN, which means you again enable the interrupts, but before you enable the interrupts, you just restore. So you just restore whatever is present in whatever has to be present in the program counter, which means earlier you have saved this particular address, right, 101. Now you store it back in the program counter so that your program will again start from the address 101. Got it? At this point, you can let the interrupts again come. So here you have cleared IEN. Now again you are setting it back, right? So see this. Whenever we are actually there are some certain tasks during which we should never be interrupted. Which means when we start performing those tasks, no one in the middle should disturb you. So for certain, no, that is called generally, that is called as atomicity, right? Atomic units. So during that thing, that part, we are actually disabling the interrupts and again enabling the interrupts once that is done. If you observe it, at the end of the interrupt cycle, we have disabled the interrupts and again we are doing certain actions, and during these actions we don't want to be interrupted, because if you get interrupted in between and if you go to some other again interrupt handling, then what happens is this will lead to ambiguity, which means there's a chance that this particular request will be lost. That is why till you perform these actions, we are going to disable the interrupts and again set it only after to do it. Similarly here also we are again disabling it and again enabling it, right? So all these things have to be done as a unit, single unit. Got it? So anyway, these two things are actually done in the software, right? And they are disadvantages in the sense we don't want them. Okay, fine.
Concurring